Hello. So I hope everybody's having a good time. Okay. Can everybody hear me all right? Sometimes I talk too loud, but I think it sounds good now. All right, so today my goal is to persuade everyone to take a look at the Netsniff NG Toolkit. And we're going to go through a bunch of examples and some features of the toolkit. And hopefully we have some developers in the crowd. I'm not so much of a developer, but I am trying to learn various things like C. And maybe we can convince some of you to contribute back to the projects. I think there's some really interesting things going on in here. Okay, so I actually, in my biography on the website, it says I was an admin for a small business. Well, actually I just took a new job, so it's been a rush getting all my stuff together too. I just moved a few months ago, so I'm now at CSA, which a few of you may be familiar with is for our involvement in the Bro project. The Bro network monitoring platform, we work on that, so that's pretty cool. And there's a few other things about me. I do a lot of documentation mainly for the Netsniff NG Toolkit. Okay, so let's get started with the topic. So it started in 2009, and it's basically done out of the free time of the two main developers. There's been some work where we've had a few other guys from industry where their reporter would help them do labor time to contribute back if they needed something useful, like wireless RF monitoring and such things like that. So it's basically been people contributing to the free time like most projects. And even though it started in 2009, it's still in its infancy. But now we're at a good point, which we'll talk about later, and to where we're developing, or it's at the point where there's a lot of features, very stable, and so on and so forth. So you can use the toolkit for network analysis, packet sniffing, traffic monitoring, security, all kinds of stuff like that, performance metrics. So the toolkit has a bunch of tools, and today, you can quickly read over these if you need to, we'll talk about 4 of them: Netsniff NG, TraffGen, BPFC, and FlowTop. And those are the main ones, particularly the Netsniff NG, TraffGen, and BPFC, but I will mention FlowTop briefly. So this is the big picture. So that if you want to categorize this and what each of the tools do, this is how you would do it. This is a nice little graph that one of the guys created. So over in the traffic capturing and traffic generation areas is where we'll mainly be staying and talking about. So this is basically, we use in Netsniff NG, we use memory map buffers using on the PF packet sockets, where the trap or the packets are memory mapped from kernel space to user space. You don't have to do extra context switches or anything like that. So this is about the best performance you can get from user space. And there are third-party drivers like the Mirror Sniffer 10G, and you guys may be familiar with PF DNA. Those tend to outperform because they do custom things, and they have specific hardware drivers for those cards to get extra performance. So one cool thing about TraffGen, which we'll get into, is you get entire control over the packets, all the headers, all the data, and the toolkit is optimized for Linux. They're not interested really in porting, but if someone else will do it, they'll probably gladly accept it. But it's optimized for Linux, and has a very small code footprint. So, and like I said, we're at a good point in its life cycle. The reason it's optimized for Linux is that the core developers in Netsniff NG are kernel devs. That's what they do. So they're usually on the latest features of the kernel, and you can see one of the kernel is contributing back. And I'll go through a few of those. And if you're wanting to get into some usage examples, some of the latest features in the kernel, a good idea is to actually just review the Netsniff NG code, because they usually integrate it when they find that it fits, and it's there right away. An example is this is tpacket v3. So this is a new structure for packets, and it was developed by Chetan Lok, and it replaces tpacket v2 in the kernel. And basically, the results, which is the important part for many of us, is just that there is a 15-20% reduction reported usage in CPU usage and a 20% increase in packet capture. And the only sniffer that has this that I'm aware of right now is the Netsniff NG Toolkit. So Netsniff NG is the sniffing tool of Toolkit. And any program that uses libpcap is using tpacketbc because we're using that library. That's what they have to use that version. So and there's a few reasons at the bottom. So packet density is increased, packets are closer together, and there's less misses in the TLD. So CPU can have more time to processing without missing the cache. So another development that was recent, I believe this is from Daniel, one of our core developers in the kernel, is this neat little Vpf instructor. This allows someone to, it's a dynamic instruction, to actually write packet headers to disk with just truncate the payload, just skip it, which is pretty cool. Because before you would have to do probably some math, you want to do it in the entire header, you know, the 20 byte IP header, blah, 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 the 8 byte EDP and stuff like that. But now you can just enter this and dynamically does that. And basically at the bottom, in the example, we have you load this value, whatever the value represents, OFF, that's what they're calling the instruction, BPFC. You return whatever is in the accumulator, that would be the value that basically specifies the size of the packet to return. So, which is pretty cool. And again, the PCAP does not have this, and BPFC is the only one aware of that does, unless you just write your own code to do it. So, and this is a new thing. This is also done by Daniel, where they actually have a net leak monitor. So you can actually, they have net leak, so you can actually snip on a PF packet socket and listen to net leak messages, which basically is how programs talk between kernel space and user space. So this is packet analyzer neutral, so we're actually going to have a plan is to have a dissector sometime in the future so people can analyze those messages in Netsniff. Okay, and let's get to Netsniff in particular. So it's an analyzer, recorder, replayer, and you'll see this on the website, the man page. It uses the PF packet socket with nmap, RX, and TX ring. At the time it came out, it was the first tool to use that, so you'll still see using that. It's not too much of a big thing anymore because like libpcap and all those tools that rely on, they use, because of that, they use the RX ring. Anyways, so it is now Netsniff is a backend recorder for Insecurity Onion and Explico and the Network Security Toolkit distribution. So if you're using Security Onion, I'm sure there's a few users in there. Anybody got hands? Raise them? Yes, awesome. I love Security Onion. So you're using Netsniff in there as well. And we support, our Netsniff supports a few different I/O methods, which is nice because a lot of the tools you don't get the different I/O methods. And you get rewrite, most of the tools use that. The standard rewrite calls. Here, Netsniff defaults to scatter gather, which is a little faster, because it bundles up the calls and uses vectors. And nmap is another faster than sequential I/O, or it is sequential I/O, I believe. And that's if you can fit things in RAM, you should use nmap, because you'll get better performance. And we also, the Linux kernel has the JIT compiler, and it's not enabled by default. So when you run Netsniff, what will happen is it'll enable the JIT compiler. It's just a setting in procfs, or you can use syscontrol if you just want to add it to the file. And basically what the Vpf JIT compiler does is that it creates a JIT image based on native code, or native based on your architecture's code. So it's native. And then the result is that it compiles that, and every time a packet comes in, that gets executed against that code. And then because the code is based on your native underlying architecture, you get about, it's estimated about 50 nanoseconds extra performance over the normal Vpf compiler. So you use JIT, you get a little better performance and execution of the packet. And it also does some basic OS tuning for a reception. Whenever you run Netsniff, it'll go through a few options in procfs, like the RMEM and defaults and max settings in the WMEM, which basically just controls software memory buffers, and it increases the sizes. Okay, the Linux kernel supports a few packet types. So basically, when you're calling the socket, you can say, oh, here, apply only host traffic or broadcast traffic or multicast traffic. And in Netsniff, you just add the dash type. You get outgoing, others, multicast, broadcast. So you don't have to do a Vpf filter, really. You can just apply these types and get the same result. Okay, so we've got a few examples here. The first one shows a basic usage and how if you want to do full content daily capture, you just say, hey, First, I should note that it's really easy. So you just have in and out. It's pretty much the things you need to know. It's pretty intuitive. So in on this interface, out to this directory. In that case, it's just out to pcaps. And we use silence because we don't want to print the packets to the screen, because that will cause a number of interrupts because it's got to print to your terminal. And then we allocate a RAID buffer size of 2 gigabytes. And so in this example, we say, hey, we're run it as high priority. You can also recognize if you're run it random. And then we say we're going to run it at an interval of 24 hours. So every 24 hours, we write out a new PCAP. So you have daily PCAPs, which is kind of cool. So got that built in. Here's a few other examples. We can use RF raw. So that basically puts your device in a monitor mode for using wireless. You can sniff raw. We can also replay from interface to interface. And at the bottom, I'm going to show a few examples of applying filters. And I will mention that Netsniff does not completely rely on the libpcap in the sense that it is compiled with libpcap, but we don't use the libpcap calls to open a socket, read a packet, and so forth. We actually just use it if someone wants to specify a high-level libpcap filter, like TCP and port 22, like I have listed. It'll actually just go to libpcap and compile that. So otherwise, you can use BPFC. Okay, here's a little output at the bottom. I'm not sure how readable it is from up here, but generally we have at the top you use the verbose option. It gives you a few things, like how many frames can fit in the buffer and so on, based on the size of your buffer. And you can see the dissection in the middle box, and it also has GeoIP built in. So at the bottom you can see, you may be able to see, it says that it detected a location in Sydney, Australia for the destination, which is kind of cool. So that's built in. And the statistics, it gives you, which everybody's quite familiar with, incoming pass filter dropped, and then a percentage in the capture duration. Okay, so let's go to TrackGen. TrackGen is a multi-threaded number generation tool. And basically, you create a packet based on TrackGen language. It's got a few expressions. You basically just specify the hex values, and you can generate the packet out the interface, which is kind of cool. It's more flexible than that, though. There's a few macros and things that make things easier. And here's a test that the developers did when they were doing this thesis on traffic generators, and you can see PacketGen is well known as one of the fastest one if you don't have a hardware generator. It's a kernel module, and you can see that TrackGen is fairly distributed, not quite there, but very close. And is anybody familiar with PacketGen? Okay, it's a pretty cool in kernel modules in the source tree, so when you install the Linux kernel, you should have it installed. You can just load the module, and then I'll give a few examples. But let's take a quick dichotomize this and give a quick overview of each one. So PacketGen is typically faster on small packet sizes and nearly the same otherwise. TrackGen is not quite as fast on the smaller sizes, like 64 bytes and 128 bytes. But as it rises, as the size rises, it's much easier to generate traffic because it is hard to generate small packets at a fast rate. And here's an example. On a 64 byte, on one of my tests, I was generating 520,000 packets per second, and PacketGen during the same test was 620,000. And the cool thing about TrackGen, though, one thing it has as an advantage is that the entire packet is customizable. The payload and everything, and that's not the case with PacketGen. You have a few options, and then you cannot really go any more granular. So we'll check that in a second. And then PacketGen is configured by sending commands to broadcast. So it's usually a shell script that floats around the internet. Uses the PacketGen commands. You just set the command or the number of packets you want, all that. And the shell script does it. Just basically echoes values to broadcast. And you can find that on the web. Where in the case with TrackGen, what we do is we have a configuration file, and basically we just say, hey, we make a heading delimiters, anything between these 2 points is going to be our packet, and then we just type it out, and then we generate it. And here's an example, this is using a 64-byte frame of PacketGen, and here's me not using the script, I just figured I'd show you how it normally does. So just echo these values, and here you have source mag, destination mag, UDP ports, min max port. So you can do ranges. Here I don't want to do ranges, I want to generate the syslog 514. And that's basically how much granularity there is with PacketGen. However, with TrackGen, we can do this, which is cool. Now, this takes a long time doing things like this, obviously. But with the macros, we can speed it up. Now, here's some performance metrics. This was at my house. It's at a server I was using lying around. It's approximately 6 to 7 years old. So I know that it's reported from multiple people that we can do line rate, 1 gigabit line rate with TrapGen. I don't want to work any 10 gigabit per second performance metrics yet, but if I get my hands on some stuff that are on modern machines. I do have an example at the bottom, but like I said, my machine's 6 to 7 years old, still power edge. But here's what I have. You can see if you look at the 1 gigabit rates, we have, with the 64 and 120, you can see how the line rate percentage increases. So 64, we have 24% of the traffic generated was at that line rate. So, and we see that we're nearly our nearly line rate as we get to 256 and above. So we get pretty close in the 90% range. However, in 10 gigabits per second, it's much, much harder. And I think on my test with the package end for that 64, packet might have 3% with TrapGen. I was able to double that with packaging. I was able to get 6% of line rate with packaging. Okay. 10 gigabit again is pretty hard to do. Okay, so let's look at a few TrapGen examples. So the first example we have, we're sending 15 million packets from reading in from this config file. That's called a 64.cfg, and we're outputting it to D2. And that's really all there is to it. So it's pretty simple to use. So once you have your configuration in place, you just hit enter and they're out. I've sent out the interface. And then we also do mortality tests. So basically, if you want to fuzz a kernel or a network stack, you can do that. And you can also do with there's an option for setting a seed. And then basically, after it runs, it'll test, it'll do like an icing the echo and see if the kernel responds still. So. We can also generate raw inter-tutorial 11 frames, which is nice. So you can do your raw inter-tutorial 11 stuff like beacon frames. You can just send those out, which I have a script. I'll show it closer to the end where I've written something like that. We can also pass through STDN, where we say TrapGen-E. That's a built-in TCP configuration. So basically, what we do is we just pipe that into TrapGen. We specify on the next instance through the pipe the in, you put the dash. It's going to read into that configuration from standard in, and then we'll output it. And here's a little look at the TrapGen expression. So we have these macros, fill, random, dynamic random, constants, different ones, we've got incrementers and decrementers. And we have a few examples here. So if you look at this under the macros, number 2, fill. So we can fill, an example I have XFF. So the full byte, all the bit sets, and we want to generate that 10 times. So 4 n bytes generate this. And you can, so if you want to generate a 64 byte packet real quick off top, instead of doing a whole configuration, all you have to do is say fill 0xFF, comma 64. And then you generate 64 bytes of FX. So not bad. So for different types that TrapGen accepts, we have decimal, hexadecimal, octal, binary, and characters and strings. So we can specify things in other ways. You don't have to use hex. This is nice. Again, we can actually use the C preprocessor by passing the -CPP option, and then we can use definitions. And you see definitions. So we can include, TrapGen comes, when you install the Netsniff Toolkit, there is a file, stddef.h, that has a bunch of definitions already. So you can just include that. And the example at the bottom, we have the protocol field in the Ethernet header, eth_p_ip. So if you don't know that you want to put IP above, you can just put in that definition. And it'll translate it. So here's how this is basically a packet definition up here. You have the curly braces, beginning and ending, and the packet data goes in between. Not too bad. So here is that example I was talking about earlier. If you want to read 64 byte packet of all Fs, and here you go. That's all you have to do. Stick it in the file and tell TrapGen to read it. And we have this one. This generates 512 bytes of random data. And you can use your scripting languages. So if you guys want to make your own configs, like here's an example of Python, just kind of using Python print statement just to print the brackets, new line, and then add the data, and then multiply whatever happens at my packet times 8, so that string 8 times. And basically this, so that's what I got. And then all you have to do is send that with TrapGen, and then here I use Netsniff NG to read it in. And you can see that whenever there's the ASCII translation at the bottom for the characters, you can see my packet, my packet, my packet. And the beginning part of it is actually in the source, or the source destination MAC address. So that's the other parts. That's why you see the cutoff of the ETA. So pretty neat. And here's a little more advanced traffic expression. So here we can actually tell traffic, hey, what CPUs do you want to use? Here we use 0 through 3, so 4 CPUs being index 0. And we say Ethernet, we want to generate 12 bytes, so the source and destination Ethernet max hardware addresses, and then we say, hey, after that, we want to use the IP protocol field, so we specify that in there, and then we want to generate a IP header of 20 bytes, random. Fuck's going to be valid, but hey, we can do it. And then we'll do a IP header of 8 bytes, and then for the payload data, we'll for 1472 bytes of random. So the random functions are good with functions. All right, so here's another example. A little more advanced. So basically what we're using is the built-in function here. See the top says trapgen-e. Well, this is the built-in TCP example, and it has a full-length packet that is valid. You can send this out, and it's supposed to be include the SDDEF file, the header file, and then we fill in the destination MAC, source MAC, protocol field, IP version, the international header length, type of service, the total length of the header, and so on and so forth. And we actually got a macro for checksum, so you can just do csum IP and then specify the values based on the size, TCP ports, blah, 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 and we can set the flags. So we use bit shifting over here, it's a little more advanced, but all that can be done. Now, if you want to use them in conjunction, our PCAP2 trapgen, this is nice. If you have a PCAP file, I'm sure many of you are familiar with TCP replay, well, you can do something similar with trapgen and SNFNG, or with SNFNG. What we'll do is, first, we'll have the PCAP, we'll write to disk, and then we'll pipe it out to trapgen. And you can again apply a Vpf filter in the bottom. I say, hey, read in this PCAP file, packet.pcap, send it out via STD out, and we want to take one packet of it, and then just we want to use the Vpf filter for the first TCP packet in the packet file, and we pass the trapgen, and say, hey, generate that packet 1 million times, and we do. And we're hopefully going to have some more. We don't have, as far as the TCP replay, we get all the specific options of the performance, the speeds, and all that. We don't have that granularity of traffic, and that may be something to think about. So, just FYI. Generative config is a little shell script I wrote, and basically what it does is I have a bunch of packet configurations, or a few packet configurations that I created, and I just stick them in there, and then I just pass some options to the command line, the arguments, and say, hey, I want my source IP address to be this, my destination IP address to be this, my MAC address, blah, 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 and port. And then it'll generate a custom configuration. I did for performance metrics, if you guys ever want to do that, I did the RFC 2544 Ethernet size frame steps. That's the benchmark methodology for Ethernet and a bunch of other network technologies. And basically, so if you just run that and you specify the IPs that you need to send to the machine and test it, it generates the entire set of 64, 128, 456, blah, 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 packet sizes that are used for performance tests. So you can just do that. I have my GitHub link at the bottom. So you can check that out when you use it. If you want to contribute back and make your own configuration, or if you have something that's useful, just pass it back and I'll include it, or you can. All right, and I also have one thing that's kind of cool is the beacon frame generator. So if you want to generate, mass amounts of wireless beacon frames, you can do it. And I currently only have a 8-byte character limit because I didn't want to do the math, or I haven't done the math yet for calculating so that the header comes out valid and all that. But so you can do free Wi-Fi in that case, so you can send that out. And it's back to the performance metrics. So how would we want? If you want to do metrics, how would we proceed? Well, this is one way. We could do we use the RFC 2544 generation set for frame Ethernet size. We can use traffic. We can basically say, hey, let's generate a bunch of traffic to the machine that we want to send it to, that we want to test the performance of. And then what we'll do is we'll run IFPPS, which is again included in the SFNG suite, but we'll talk about that. And that will actually measure the line rate as a nice option now. It's new, it's -P, capital P, where you can actually test the percentage of line rate coming in, so you can measure it that way. And we can then, if you want to do packet capturing performance tests, we can actually script, have Netsniff run in a shell every 5 minutes or something, and have your trapgen instance transmit every 5 minutes, and then you have a script that says, hey, sig int every 5 or whatever, how long it's going to take to send the packets to the process of the snipping. So you can TCP up all those if you want to test them. And then what you would do is you have that right to a PCAP file. You can use cap info some off later on just to pipe out, the loss metric and all that. And you can also pull the information from your driver and do performance tests that way. That's something I'm kind of working on. I haven't had a whole lot of time, but it will be done. So eventually I will have TCP dump, cap, build, daemon monitor, and tests and compare. So that will be coming out in the future. All right, so here's another example of the daily PCAP options. So here I put a lot more options, or Netsniff NG options in there, just so you get an idea of a few of the things that I was working on the fan page right away just for the presentation. So you can do prefixes. You can call it, hey, I want my package to begin with this word, my packet, timestamp, .pcap or something for each one, and just increments the timestamp. So things like that can be done. And here we can also set SMP infinity, IRQ infinity, and so on. So when doing high performance packet capture, I think that's what a lot of people are interested in when they hear Netsniff NG, or that's why they go to it. And it's very hard to do. I've done a few tests, and it's a lot of system tuning. It's really, really difficult. You have to do a lot of tests on different buffer sizes, network card settings, kernel settings, socket settings, so on and so forth. Even if you're writing a disk, like PD flush, and all those dirty ratio settings, you gotta play with that. It's really hard to do, but here are some considerations if you're gonna do some performance tests. One thing you should probably have is a network card that supports NAP, the new application programming interface, which basically handles the interrupts better than they were handled before in throttling. Most modern cards have multiple queues, right? So we can use RSS, which is receive side scaling, and essentially, say a DIC has 4 queues, what can happen is the packet can be split to different queues. And we can use RPS. RPS is receive packet steering, and I have there's a document in the Linux kernel source tree in the documentations directory called scaling updates, and it explains all these. And if you don't have a card that supports RSS, you can use RPS as neutral, and where you can assign queues. You can actually take the packets in and have them flow or balance kind of over your different CPUs, so you can set that up. And other things to consider are offloading measures. Usually offloading is a good thing to have. Performance, interrupt throttling, coalescence. You should have multi-core CPU, lots of RAM, hardware locality settings. You should check out SMP infinity. Fastest configuration is very important, and so on and so forth. Don't spend too much time on that. And software configuration. So if you want the latest and the greatest, like all those new features I talked about earlier at the beginning, the Linux kernel, like TPACK v3, the new Vpf Instructor, and so on and so forth, they are in the latest kernel. So you'll have to recompile the latest kernel and install it, and you'll be able to use those features. So when you're doing tests and you're doing your bleeding edge stuff, then it's good to have the latest kernel, latest mainline for the latest fixes and features. So here's just a few options. Our ideas you can use to set or to tune your system. So here we increase the memory buffer with syscontrol. We increase the queue length. That's the driver queue length by ifconfig. That's actually that's the queue disk length. Take that back. So we use the default is queue disk FIFO, fast, fast, something like that. So you can set the value of that. Set IRP affinity. You can enable the JIT compiler yourself. Just echoing a 1 to the file and lock at that, so on and so forth. And you can, if your disk is too slow, which is the case for many of us, you can use a RAM disk. So you can just mount a 20, here this is available, mount a 24 gigabyte RAM disk, and then you can write to that. And then later on, move it over to your hard drive and at night or something, and then travel over to it. And BPFC, so this is the Berkeley packet filter compiler. I believe it is written to standard for the BPF paper that came out by Van Jacobson, and his name is escaping me at the moment, but I believe it falls into a T. So we have support for internal Linux kernel extensions. So these are things that the Linux kernel supports that give you lower level filtering access to the packets, and I'll show a few of these in the next slide, I believe it is. A lot of the libpcap compiler does not have those built in, so if you want to use those extensions at the moment, you need to use BPFC and keep it up to date on that. Also, we can use BPFC, you can use set comp filters, where this is something kind of new to me. I found this out not too long ago, where Google Chrome uses this, where you can actually filter on system calls. So if you're using Google Chrome on Linux, that is, of course, because this is a Linux thing. And so does SSHD, and I believe that's from the Open SSH project, that SSHD. They use these as well, where you can actually apply Vpf filters and filter system calls, which is really cool. It's kind of like a sandbox. And then NetFilter actually has, or IP tables now, which you use to access NetFilter, has a feature. You can actually type in or read in a Vpf file, so we can generate a Vpf compilation file, or compile Vpf code with Vpfc, and then pass it in IP tables. And it actually can output in the IP tables or NetFilter format. It's pretty specific. And here's an example. So we have a Vpfc, we have a Vpf file called ARC. They're basically compiling and taking the output and writing it to ARC.vpf. And then tell Netsniff that you to read it. So if this is also a really good tool to learn how to write Vpf, because you really can't do that on the VCAP, right? You just specify a high-level filter and it compiles it. Of course, you can dump the assembler-like code, but here you can actually write it. So, like I said, some kernel extensions that can't be expressed in the high-level syntax can be done in this, and there's a lot of other things that are instructions around in the VCAP. So. And this is mainly used for kernel devs to do, like there's bugs found, they'll use this to test this compiler versus if they're wrong. So, and here's some of the Vpf extensions. So you can use packet length, you get the proto, which is the ETH type field, type, POFF, when we talk about detecting the payload, interface index, VLANs, queues, CPUs, and hashes. There's are RX hash ones. You can, if you're using RSS, which is what I was dealing with, it generates hashes to balance the traffic. You can actually filter on a hash. It's kind of cool. So here's how you compile it. So at the top we have on the PCAP equivalent. So we say ether to source. Anyone reading this map? Source address. So A, B, C, C, D, E, F, F. PC will follow. And Vpfc is a discrete text file. And I say load LD. This is going to load 4 bytes. It is a word. At the 8-byte offset, which in Ethernet, the frame, it begins with the destination MAC address first, then the source. So we'll fill the source. So we want an 8th in, and we'll have 4 bytes left because the Ethernet MAC address is 6 bytes. So basically, that part will load the 4 bytes. As you see in the next instruction, it says just or jump if not equal. So if it's not equal, then we'll go to the drop instruction, which is at the very end of the chain. At the very bottom, we say if it jumps to that, then we'll return the 0 length of the packet, so don't return the packet at all. And then if it is equal to CCDEFF or MAC address, then we'll jump to the next instruction, which is load H. We're loading a half word there, 16 bits, 2 bytes, and we're loading the other 2 bytes. This is based on the Indianness. So AABB, that's the rest of the frame, or the MAC. Source MAC portion of the frame. And if that is equal, then we return 1514. If that is not AABB, then we'll return nothing. We don't match the packet, we don't return these. And this is what happens after you compile. So you get the ugly outcomes. You can use TCP dump, use dash T to dump high-level filters to outputs as well. And here's an example using a kernel feature or the extension. This is actually the filter on CPU. So we load the CPU value. And we say jump if it's equal to CPU 0, then we'll return. And negative 1 is just another way of saying return the entire thing, no matter what the size. So we don't say 1514 where the frame's even bigger than that because general support. And negative 1 returns the entire thing, no matter what. Otherwise, if it's not CPU 0, then we'll return. So. And the example use case for this is if you're using RPS where packets are distributed across different CPUs. You could then use the filter like this to say, hey, I just want to grab the packets that arrived on this CPU when they're distributed. And then to run this suspension, you say, hey, take it in and apply it. And it compiles to the kernel and you get your packets. And here's some notable examples. So where the Netsniff Toolkit was used. And 2 examples that I'm aware of. is that one of the kernel developers found a performance problem in the fragmentation of the Linux kernel, and they were able to use TrapGen to create the packets to test that, and then later on they encountered some problems and they made a patch for it. And VPFC was used to prove and exploit a x86 JIT bug. So plug in the JIT compiler, someone used VPFC, and found out that they didn't match. That whatever that was compiling in the JIT into the VPFC didn't match, and it turns out there was a bug in the JIT. So Hyatt PPS, or IFPPS, is another cool tool that just reads stats. And it reads it directly from the kernel statistics, all the proc files. So, for example, if you want to look at your network statistics, you can just do a watch on cat-proc-net-dev, and that's got all your receiving packets, the bytes, the drop count, the errors, the frames, all that. So you can just read directly from there. And that's what IFPPS does, along with a number of other places in the kernel, like soft IRQ, and proc interrupts, and so on and so forth. And with this, since we don't rely on another tool, we're doing directly from the kernel statistic, and we can use a library to make other calls, we actually get more accurate results under high speeds, high throughput. Because an example was on one of the devs machines where they were generating line rates on 1 gigabit Ethernet. IP track, which uses lit PCAP, was only reporting 246 packets per second, whereas since they were reading directly from the kernel stats, IFPPS reported the full line rate. And we use this in conjunction. Basically, all the stuff that you find using the normal system things like VMstat, all that stuff's printed here, so you can monitor context switches, idle time, CPU time, idle wait time, all that stuff. So when you're using network traffic performance or measure for that, it's really nice to you can output it to the new platform. So here's a look at IPPS. This is not really fancy right now because this machine just has a single CPU, and as you increase the hardware, the display gets bigger, you see a lot more stuff. So that is generally IPPS. It just runs at an interval, and the default is 1 second. And we can actually output the CSV, which technically it's not CSV, that's what they call it. And basically it's a white space delimited for GNU plot. And here's an example where I'm reading a IPPS CSV file, and I'm just saying, hey, print all lines that match the packets per second, which is the third field. And here, we can use GOP, because it has a timestamp function, where we can say, hey, you're reading this timestamp, convert it, so I call it unity clock time. And here we say, hey, print every line or interval that matches, or where the drop count is greater than 0 and the errors are greater than 0. So we want to know if we drop packets for our testing interval, and we can see here at the time we converted it, and blah, blah, blah. So you can hack that easily with GOP if we need to. And here's a quick GNU plot chart of a test I did. And I just if you want to play around with that code at the top, I've just begun to use GNU plots. These are fairly rudimentary. But essentially, we're just hitting a run, and you see the chain, or the top green line, as it goes over, that's where the TrapGen ran start. And from another machine, and this is on the capture machine, this graph is generated from those stats. And we got about 650,000 packets per second, and then we had a loss of like 50,000 drops from the kernel. So you can graph that, and you can go a little further, the same file generally, and just say, hey, look at the drop count, and you can see that it's a little less than 40,000. So then you can show that you can put the time on there, and you can correlate with IPPF stats and see, if the CPU time spike moves a cron job in the background, if it's the CPU time or something at that time. So you can just correlate all that information because it's written. And then the other tool we'll talk about is FlowTop. So FlowTop is a top-like NetFlow viewer, or connection viewer. It uses net filter. So basically, you say an IP tables command, you say, hey, pass in all this traffic, and you run FlowTop, and just anything that comes in that matches that match rule, and it links, or that's how FlowTop makes call to net filter. And basically, it actually gives you a nice little flow. This could be good for instant response, by the way, because it actually tells you what program on the machine that you're running it you have to generate the traffic or is receiving the traffic, which is really cool. So I appreciate that. And eventually, there's going to be some new features on here like sorting on bytes, and packets, and all that. So it also does geo IP location. As you can see, we have Sacramento, California, and Mountain View, and so on and so forth. So it's pretty nice. And to install this FNG, if you're running Ubuntu, this is generally all you need. So let's put this slide up. Not too bad. And what could be next? Well, we have a few things that are going to be worked on. One thing we're kind of excited about when it comes out is the packet fan out, where you can fan out packets to multiple sites, have multiple listers, and distribute the load of packets across multiple instances. So it's something that we look for that's fairly new in the kernel too, so I don't know what the stage level that is. And then basically, pretty much everything else I mentioned, like the flow top and like some packet counters, and there's going to be mouse out or mouse on. That program is a nice HP-like program where you can generate packets at a higher level, so you can generate some stuff. And it's got a bunch of dissectors built in, so where you just say, hey, I want to generate a syslog packet, I specify the facility, the severity, blah, blah, blah. Just sends it out. So you can do cool stuff like that. And that is a tool that's been picked up of the man that developed it. We originally passed away 2 years ago, and so they're trying to integrate that into the toolkit now, taking up his code. So it still needs to be improved. And there's a bunch of links if you guys have any for more thorough research information. You can go to those. And if you want to look for flat configurations online, not a whole lot there yet, but if you use those Google dorks at the bottom I put on there, you can probably find some filters or some trapjet files. All right. Do I have any questions? No questions? All right. Well, I hope you guys check out the toolkit. If you have any questions, do email me or email the list. Preferably the list, unless it's more personal to my talk. And I guess that'd be about all. Well, thank you guys.